Okay, so welcome back. Now let's continue from where we left off. So we have been talking about Turing machine variants, and what we have done so far is, well, we had the standard model, so that's not really a variant, but it's just the models that we've been talking about. So standard model. Then we did the multi-tape model, where we can have any number of tapes that operate independently of each other. And now we're going to be talking about the non-deterministic model. So remember that the transition before was delta is a function from Q cross gamma to so remember that this was the state that we were in, so state before. This is the symbol red. And once we know those two, we know exactly which state to go. So the destination state, as well as what symbol was written. So symbol written. And whether or not to move left or right. So this was the transition function we had before. And then all we really are going to do in this model, the non-deterministic model, is the same stuff on the left. So it's kind of like a PDA or an NFA. The stuff on the left side is exactly the same. There's no epsilon transition here because every spot on the tape always has some character in it. But then the right-hand side is going to change. It's going to be the power set of what we had before. So Q cross gamma cross LR. So it's exactly the same model, except now we can go to any number of combinations of states and things that we write. And we will always choose exactly one of those outcomes, if there is one to choose. And our notion of accept is a little troublesome if we're not careful. So we're going to accept a string W if and only if there is a sequence of non-deterministic choices that we could ever make to get to Q accept. So that may seem not very controversial or important, but it actually is, because it could be that a lot of possible choices we could make and have us end up in Q reject. But as long as one of them in some way allows us to go to Q accept in some configuration, that's all we need. And but also we need to have a notion of recognizable and decidable. Well, recognizable is exactly this condition. So it recognizes a language. The language will be the set of strings that are accepted, which is this notion of acceptance. But deciding is a little strange because, well, in the normal model, in the standard model, it either runs forever or doesn't. So it's fixed. It either runs forever on some string or it doesn't. But here, depending on the choices that are made, it might run forever or it might not. Because for the notion of rejecting, if a string is not accepted, it could either go to Q reject from some choices, or it could just run forever. So we have two possibilities there. But our notion of deciding is going to be this. So so I should say that this is an NTM, so non-deterministic Turing machine. So an NTM is a decider if all computation paths halt, which means goes to Q accept or Q reject at some finite number of transitions we eventually get there. Okay, so we will actually show here that non-deterministic model doesn't actually give you any more computation power than the deterministic model. So what we're going to show you here is that a deterministic Turing machine we can convert into a non-deterministic one. And this one's actually easy because the non-deterministic machine, like every other one we've ever seen, doesn't have to have real non-determinism. It could just do exactly one choice like the deterministic model does. So every deterministic machine is already a non-deterministic one. So how would we show that we're given a non-deterministic Turing machine and we want to convert it to a deterministic machine that does exactly the same thing? So if this guy accepts string W, we want this one to also accept W. And if this one rejects W, we want this one to reject W. And also, even more than that, if this runs forever on W, we want this one to run forever on W. So we want the behaviors of these two models to be identical to each other. So how would we actually show this? So we're going to be using something called the computation tree here. And it's kind of like the parse trees that we've seen for context-free grammars. For context-free grammars. So what are we going to do here? What we're going to do is basically that. But now we're going to basically have a node in the tree for every configuration. Actually, no, this is not what I meant. It's not computation tree. I get these mixed up a lot. So this should be configuration tree. So what we're doing here is we're going to plot in a tree the configurations that could ever appear in the computation. So at the top, we have the start config, which remember is always going to be Q0W. But in the non-deterministic model, we could have any number of choices. So let's just say in this example, there are three possible choices of what the next configuration could be. And we could take any one of them. And then maybe the one on the left has exactly one choice. Maybe the middle one has a whole lot of choices that could be made. And then maybe the last one has only two. And then maybe this one also has one. This one has two, but the one on its left has none. That's its endpoint. And then maybe we have three on this one, and etc. So we're going to have all the configurations possible after one transition right here. And then this one is two transitions, etc. And one thing that we should note here is that the tree could be infinite, right? Because it could be possible that that this machine could run forever on this string. It could be possible, but it could be possible that we stop early, like here, and other places. So what we want to figure out is, well, let's suppose that somewhere way down in this tree, there is a an accepting configuration way down here. But it could be possible that we make this choice, this choice, this choice, and then we could just keep going down infinitely and never hit that Q accept because we made bad choices. which is what the problem could be with the deterministic machine. We could have the deterministic machine just say, oh, just pick any one of them, but any one of the possible choices. But it could be that we just go down the wrong path and we will run forever. When in reality, the non-deterministic machine, I'll do it in blue, made a different set of choices, possibly, and it went down this path that did go to Q except in a finite amount of time. So what we want the deterministic machine to do is basically explore the entire tree. And if there is a Q except configuration at some point, then what we should do is to be able to find it. So let's see. What could we possibly do then? Well, what we can do, one possible attempt we can do is to run depth first search on this tree. But one thing that you should note here is that this is a red herring, because if you look at the red path that we did here, that will potentially go down infinitely. So we could just keep going down further and further and never hit the bottom of the tree because it's infinite. So depth first search, So depth first search is not the way to go. But if we instead do breadth first search, then let's think about it. If the Q accept is at some finite level, then would depth first search find it in a finite amount of time? And the answer is yes. Because, it'll find it eventually. Because it's at some finite level, well, at each point, we only have a finite number of configurations we could ever see. So therefore, at this point, the tree is only a finite number of nodes. So what we should do here is to run in parallel. And how does that work? What we do is this. So for I equals 0, 1, 2, 3, and there's no upper bound on how far we can go, then what we do is, so the first step in here is to run the machine on W for I steps. So the Turing machine on input W for I steps in all possible ways. So any possible choice we could ever take, we're going to look at that possible choice. So then if we get an accepting configuration, then we accept at that point. We just say accept. And we're not going to do anything for rejecting, because all that we need to do is to accept the strings in the language. So the thing that I mentioned earlier, that the behavior should be the same, is not actually necessarily true. That's something we would want to happen, but it's not necessarily what we need to happen. Well, if it accepts W before, it should accept W now, because we need to have the same language. But could it be that if it runs forever on W before, it's not going to run in a finite amount of time this time, because I'm just simulating even more. I'm doing even more work. So it can't run in a shorter amount of time. But if I instead say, well, if it rejected W before, could I just have it run forever on W now? And the answer is yes, we could do that if we wanted to. So we could actually cross out rejecting W here. Explicitly rejecting W here. We're implicitly rejecting W by, we're implicitly rejecting W by running forever. Why is this sufficient? It's sufficient because if it doesn't accept W, I don't care whether it outright rejects W or it runs forever. It didn't accept W, which is the case here. If there is no accept configuration at some point in this tree, then we will run forever by this algorithm right here, which is exactly what we would want anyway, because there's no except configuration in the tree at all. But if there is an except configuration in the tree, at some finite level, we will find it, which means we will accept. So, for that reason, this deterministic brute force Turing machine will accept the same language as the non-deterministic Turing machine. So the fact that we were able to keep track of all of the possible things that could ever happen is quite important here. So what we can get out of this is that non-deterministic Turing machines are equivalent to deterministic Turing machines. And so that is pretty amazing to actually see. Okay, so that's what we wanted to talk about there. Yeah. Okay, so one thing that we should talk about here is a completely new type of Turing machine, which is a little bit different. It's something called an enumerator. So if we look at this algorithm that we have here, we have this for I equals 0, 1, 2, 3, blah, blah, blah. So how does that actually work? Like if we wanted to really do this in reality with a real Turing machine, quote unquote real Turing machine, how would we actually do this? Well, one thing that we would do is we would have some kind of counter, right? We would just say, we would have, let's just say like in binary, like the first time we have 0, and then we have, let me do it this way, then 1, then 1, 0, then 1, 1, then 1, 0, 0, then 1, 0, 1, etc. So we would have a counter on the tape, and then we would just read the counter itself on the tape. So what we're really doing is, at this point, we are enumerating the integers. By that I mean, we're just listing out all of the integers in some order. So what is an enumerator? Well, we can generalize this notion of just outputting strings to a language. So we can say, well, we could just list the strings in sigma star by listing all of the strings of length 0, then all the strings of length 1, then all the strings of length 2, and just keep going on and on and on. So what is an enumerator? An enumerator for a language L is starts with empty tape. So there's really no input there, and writes this string, which is # W1, # W2, # W3, # W4, #, and it just keeps going. Where, well, I should explain what these are. So the # here is a delimiter. So just to identify where one string begins and another one ends, that's all it is. And the WI here are in L. And what do we want to guarantee about this? Well, I could just say, well, let's enumerate the integers. Well, I could just say #0, #0, #0, #0, #0, and I just keep writing zeros over and over and over. Well, that's not really enumerating the integers, because if I just write 0 over and over and never stop, then I'll never hit 1 or 1, 0 or anything. But so this is clearly not allowed. But what we're going to allow is, well, we could repeat a string multiple times. So if I print 0 3 times, and then I move on to 1, and I print it 3 times, etc., and I print every string 3 times, well, no matter what number you think of, at some point it'll be printed. And if I mess up the order, like I print the strings of like 10, then the strings of like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and then I go to 20, 19, 18, 17, etc., as long as I eventually will print any number you think of, then then this is an enumerator. So this is something we would want. So what do we want in the general case? What we want is for each wi in L in a finite amount of time, wi will be printed. Okay, so all that we are requiring here is that you pick the string that you want, or just think of a string. At some point, it'll be printed if it's in the language. If it's not in the language, it'll never, yeah, I should say that too. If it's not in the language, it'll never be printed. So if a string z is not in L, z will never be printed. So it only prints the strings in the language, and that's it, nothing else. So, and also, what should we call such a language? A language. L is enumerable if some TM enumerates it. Okay, so like sigma star, for this reason, is enumerable. Oops. Enumerable. Can't spell it after all these years. Yeah, because what we can do is just list the strings of like 0, 1, 2, etc. So you may be thinking, okay, well, we have decidable languages, which are the Turing machines that will always halt. We have recognizable languages, which is the language of any Turing machine. And we have enumerable languages. Well, are these the decidable ones, or are these the recognizable ones? What we're going to do is show that enumerable languages are exactly the same as the recognizable languages. And you can kind of see why, because if the string that you are presented with is not in the language, but you don't know that, well, you could just have the enumerator run for a while, but you have no idea whether or not it'll ever print your string. So the enumerator in this case, you'll be waiting an infinite amount of time before it'll you'll be convinced that your string is not in the language. Which is fine for the recognizable languages, because if it's not in the language, the recognizer doesn't have to halt. A supposed decider would have to halt, because that's what a decider does, but a recognizer doesn't. So how would we actually show this? So again, if we want to show that two sets are the same, we want to show if and only if. So if we have an enumerator, we want to construct a recognizer out of it. So let's see. So how would we actually do this? So let's just say that we have an enumerator E for language L, and we want to construct a recognizer R for L, for that language L, same language. So what would we do here? Well, it's exactly the idea we were just talking about. So what we're going to do is we're going to write a quote-unquote high-level description of an algorithm for a Turing machine to actually do this. So how would we actually do this here? So how would we actually say this? Well, on input W, what this means is that the recognizer gets input W. So when we say on input W, we're going to do some steps based on getting input W here. Okay, so the first step here is to repeatedly generate a string from the enumerator E. So have E generate another string, keep generating a string, if, and let's just say that the string here is X. So if the input string W that we were originally given is equal to the string that the enumerator printed, well, if the enumerator prints it, it's in the language. So then, which means that the string W is in the language L, which means we need to accept. And then otherwise, go back to the USSR. No, go back to step 1. So, okay, so why would this work? And I should put quotes here to say that we're done with the steps. So another thing I should say is that this is a high level algorithm. So this is a high level algorithm because I'm not saying like what the Turing machine is actually doing. I'm just telling you what the main steps are. Have it generate a string from the enumerator and test if it's the same as the input string that you get. So why would this matter? How do we actually show that this works? Well, if the enumerator prints the string, which means that this if condition is satisfied, then that means the enumerator printed a string, which means that it's in the language that we want, the language L, which means that the string W that we get, we should accept it because we just determined it's in the language. But if we get a string W that's not in the language, well, the enumerator will never print it, which means that this if condition is never satisfied, which means that we'll run forever. But that's okay because we now have a recognizer. If the string is not in the language, then we're not required to halt to either say accept or reject. Well, we should say reject, but we're not required to reject here. We're not required to halt. So this is a recognizer. So this is a recognizer for L. It accepts the strings in the language, and it happens to run forever on the strings that are not. Okay, so that shows that every enumerable language is recognizable, but how do we show the other direction? So how do we convert a recognizer to an enumerator? So let's just say that we have a recognizer R for language L, and what we want to do is to construct an enumerator E for L. Okay, so let's see. So what could we do here? Well, we can't just say, well, okay, let's just, so this is a bad idea, so don't do this. So this is a bad idea, which is, let's just generate strings in sigma star, which is easy to do. You just generate the strings of length 0, 1, 2, etc. And then what we can do is to run each on the Turing machine R, the recognizer that we have. And if the recognizer here happens to accept, then the enumerator should print that string. And that's all we need to do. Here's the problem. Here's the problem. Well, the recognizer here is not required to halt on any string not in the language. Well, if I generate just some arbitrary string in sigma star, I don't know necessarily whether or not it's in the recognizer's language, which is L in this case. So, but what if I just say, well, I'm going to run each of them on this machine for some notion of limited number of steps. So if I limit the recognizer to only go for a certain number of transitions, then it can't possibly run forever because I'm telling it to stop. So that's the basic idea here. So if we want to construct an enumerator, we remember that an enumerator always starts with empty input. So on empty input, telling it what to do when it starts up. And here's what we're going to do, and I'm going to explain what it is. The basic idea here is that we're going to run R in parallel for some notion of parallel. But we have to be a little bit careful in doing that. We can't just say run parallel on all strings. Well, that's an infinite number of strings, so you can't really run in parallel in that sense. But there is a way to get around that. So I'm going to I'm going to make a variable I to be 1 initially. And then while I is at least 1, and then what we're going to do is a bunch of steps. So what we're going to do here is we're going to run the first I strings. So notice that we have the variable I here. The first I strings in sigma star on the Turing machine, the recognizer that we have, for I steps each. So we're going to run them on, so for the first time we're going to run the first string in sigma star in whatever order we want, let's just say the empty string. Then we're going to run the empty string on this machine R for 1 step, and then see what happens. If any of these strings are accepted by that recognizer R, print them. And then the third step, we're going to increment the counter by 1. And that's it. So the very first time around, we're going to have the first string for 1 step, then the first 2 strings for 2 steps, and then 3 strings, 3 steps, 4 strings, 4 steps, etc. So notice that if we have, let's just say that the first string, whatever it is accepted after 1 step. Let's just say it is. Then clearly this machine runs infinitely because there's no accept or reject here. Every enumerator runs forever. So, which is fine because we're just defining a numerator. Well, let's suppose that the first string is accepted in 1 step. Then notice that we run that first string again for another step. So what I really should say here is that for at most I steps each, because it could be that the machine stops early. Yeah, so that first string will actually be printed to the tape an infinite number of times, because if it's printed after 1 step, it'll be printed when we consider 2 strings, when we consider 3 strings, when we consider 4 strings, etc. So if a string, one thing that we should say here, so if a string is accepted by R, it will eventually get printed. So why is this? Well, if the string here that we're considering, it's a string, which means that it has some placement in the ordering in the I strings in sigma star here. It is some finite place in that list because it's an enumerator for sigma star. So the enumerator for sigma star will eventually print whatever string you are considering here. And let's just say that it is accepted by the machine, which means at some finite number of steps, it will eventually get printed. It'll eventually get accepted. Well, let's just say that this string is the 500th string, whatever that means in sigma star, but it takes 5 to the 10 steps to accept, for example. Let's just say that this is the case. Well, when I is 500, this string will finally get considered, but clearly it will not be accepted for this reason. So, but the thing is, well, we're considering I strings in sigma star. Well, we're going to increment I over and over and over and repeatedly consider this 500 string over and over and over. So when I becomes 5 to the 10 to the 10, it will eventually get accepted. And because now we've finally hit the threshold for it to actually accept. So if a string really is accepted by the recognizer, it will eventually get printed. And the scenario is exactly the same if we flip-flop these numbers. Like, if it only takes a small number of steps to accept, but it's a very late string, the placement is really high, the scenario is very analogous there. So, but if a string is not accepted by the recognizer, it will never be printed because we only print the strings that are accepted. So therefore, the language of the enumerator is L. So the language of the enumerator here is L. Because if it's accepted by the recognizer, it will get printed, and if it's not accepted by R, it will never get printed. So it must have exactly the same language as the recognizer here. Okay, so what we have shown here is that recognizers are equivalent to enumerators. So you may be thinking, okay, why did you even talk about that notion of enumeration? Well, it actually becomes important later in the class to actually enumerate language or to actually just list strings. It's more convenient to actually list the strings versus just to have a recognizer for it, even though they are equivalent to each other. So it's just more convenient to enumerate a language than to recognize one in some cases. Okay, so now you may be thinking, okay, is there some Turing machine variant that is not equivalent to the standard model? Standard, and by standard I mean deterministic one-tape model. Because we did multi-tape model, that turned out to be the same. It went slower, but it recognizes the same languages. For non-deterministic, we got exactly the same set of languages. For enumerators, we got recognizers as they are exactly the same. So whatever one that you think of, it turns out that it's very likely you will have exactly the same set of languages as the standard model. And here's a reason for that. And we'll be talking about why that's the case right here. So, but we're going to take a little bit of a detour to try to talk about why that's the case. So a question you may be thinking is, that I'm going to ask you at least is, can a Turing machine given two binary, or it doesn't have to be binary, but it's just two integers, write their sum to the tape? So here we have a number, let's just say like 101 and 10, and I want the sum to be right here. So what could we do? Well, what we can do is the following. How can we actually figure this out? Well, I'll invite you to figure out, how do we decrement or increment a binary number? How do we add one or subtract one to a binary number? And supposing we know how to do that, what we can do is, let's just decrement the second number and increment the first number at the same time. So what we would do in this case is repeatedly decrement the second number until it hits 0, then not then, and increment the first number each time. Then what will happen at the end is the first number will eventually be the sum of the two numbers. Okay, because we're always adding one and subtracting one at the same time. And when the second number hits 0, we've effectively added the second number to the first one. So what would go here is just a copy of the first number. So we could actually write the sum of two binary integers to the tape. What could we do after that? Well, could we do x times y, where these are integers? And if you think about it, well, this is just repeated addition. And what do I mean by that? What we can do is we could subtract 1 from y, but add y to x every single time. So if I subtract 1 from y, and this one is the original y here, not like the one that keeps updating, but take the value of y, make a copy of it so that you save it, then repeatedly decrease the value of y by 1 until it hits 0, and just keep adding y to the first number. So instead of adding 1 to the first number, we keep adding y to the value x here. Cool. So that is actually how we do multiplication. It may be a slow way to do it, but it's a way of doing it. What about x to the power y? Well, this is just repeated multiplication. What if I wanted to do factorial? It's very similar. What if I wanted to do the cosine of a number? Well, that involves, if you know calculus, it involves a power series, which is just repeated, which is just multiplication and powers and everything. So it appears at this point that any math operation a computer can do, a Turing machine can do. So if a computer can do it, some kind of operation, a Turing machine can definitely do it. Well, what about the other way? Could anything that a Turing machine can do could a computer do it? Well, yes, because you can write a program to simulate a Turing machine. So it's possible to write a program to simulate a Turing machine. And I invite you to actually do that yourself. So let's see. So this is actually has a very famous name, which is called the Church Turing Thesis. And what did they say? They said our intuitive, they didn't literally say this, but this is, in fact, they didn't really work with each other on this, but it's just as a result of the work that they actually did. There's actually a third author, Emil Post, who for some reason is left out of this, but he did work that's equivalent to these two. They actually, what they did was Turing actually formalized this notion of a Turing machine, even though he didn't call it that. And Church came up with this notion of a lambda calculus, which is it looks totally different, but it turns out is actually equivalent to the Turing machines that Alan Turing actually came up with. So what did their work actually say? Our intuitive notion of what an algorithm is, so our notion of algorithms, and Turing machines are equivalent. So, like we just said here, it appears because we can take any operation a computer can do, we can just convert it into a Turing machine that does the same thing. It might take a lot longer to do it, and it might not look as nice, but we could do that. And we can have a program to simulate a Turing machine too. So our notion of algorithms and Turing machines are equivalent. So why is this say thesis, and why does it not say like theorem or lemma or something? The key here is, what does intuitive mean? So what is intuitive? If I had a precise notion of what intuitive is, then yeah, we could either disprove this or prove this if we knew exactly what they were, but we don't really have a formal notion of what an algorithm, an intuitive notion of an algorithm is. We kind of know what a algorithm does. It's just a bunch of steps, and pretty much every operation we've ever encountered, and in fact everyone we've ever encountered, we could easily turn into a Turing machine. So I can't actually prove this for you, but we're going to accept this because every single operation you could ever think of or ever come up with, we could have a Turing machine do exactly the same operation. So what we're going to start doing next time is we're going to answer these questions. So if a Turing machine cannot solve a problem, then a computer can't either. Cannot either. Because we're accepting the Church Turing Thesis as truth, and because they're equivalent, if a Turing machine can't solve a problem, because computers are equivalent to Turing machines, we will essentially just say then that a computer can't solve that same problem either. And that's what we're going to